Good evening, everybody. It's a stormy night here in downtown Toronto, but we are here. We are back for another episode of Cosmos from Your Couch. I'm so delighted that you guys are here with us this evening. I am particularly excited about this talk tonight. Once again, I got a little sneak peek. I cheated, but I'm very excited to see it again tonight from the Department of Astronomy and Astrophysics at the University of Toronto. We have graduate student Harrison Winch, and they'll be speaking about dark matter. This is one of the things, as the resident non-astronomer, I hear everybody talk about dark matter quite a bit, but all I hear about a lot of, what it isn't. So I realized that this must be a standard thing in astronomy. So Harrison's got a great talk, and you're going to learn about kind of why dark matter is so special and why we still struggle to understand so much about it, and so, such a mystery. So without further ado, I'm going to go away and I'm going to introduce to you Harrison Winch. If you're watching and you want to ask anything throughout the presentation, feel free to drop a comment in the chat. I'll be moderating the questions. At the end of the presentation, we'll pop back on and we'll have a great little Q&A session. Can't wait to hear what you guys think. So without further ado, let's bring aboard Harrison.
Hello, my name is Harrison Winch. I'm a grad student in the Department of Astronomy and Astrophysics here at the University of Toronto. And this evening, I'm going to be talking to you about what I think is one of the most interesting unsolved questions in astronomy today, which is what dark matter isn't. And we're going to get into all the weird and wonderful world of dark matter science and why exactly I chose to phrase the title of my talk in this somewhat frustrating way. Before we can get to talking about dark matter, first of all, I want to talk a little bit about human population. So, as most of you probably know, our Earth contains around 7.5 billion people, which is a lot of people, as I'm sure most of you are aware. And I want you to imagine for a second in your head how you would react if I told you that I had it on good authority that there were an additional 45 billion invisible people sharing this planet along with us. Completely invisible, 45 billion of them. Now imagine if I told you that, you would immediately have questions, some of which might include, who are these invisible people? Are they like us? Where do they live? What are they doing? Where do they come from? Why are they invisible? Is there any way we can possibly interact with them? And most importantly, what can we learn from them? Now, I'm sure some of you are thinking that, this is a bit of a far-fetched thought experiment. Obviously, there are no 45 billion invisible people living on Earth with us. But analogously to this thought experiment, scientists believe, for a good reason, that for all the matter that we can see and touch in the universe, all of our planet, all the other planets, the stars, the gas, the dust, galaxies, for all of that matter, we are also outnumbered 7-1 by invisible matter that we can neither see nor touch. And this is dark matter. This is what I want to talk to you about in this talk this evening. And so all the questions that you just had about those invisible people, who are they? Where do they come from? What are they doing? How could we interact with them? You should be asking those exact same questions now that I've just told you that there's this dark matter out there. And I want to talk to you this evening about how scientists are working to try and answer some of those questions, those really pressing questions of all the things that we don't know about dark matter. But before we get to talking about how scientists are trying to understand this dark matter, I suppose I should start by trying to convince you that this dark matter exists in the first place. So why do scientists believe so firmly that there's all this dark matter in the universe? Well, the answer comes down primarily to our understanding of gravity. So the way gravity is generally understood to work is that massive objects exert a pull on other massive objects. And the more massive the object, the stronger the pull. So if you have two objects orbiting around each other in space, they're held together by the force of gravity. So the stronger the gravitational pull from one object to another, the faster it will need to orbit in order to stay in orbit and not fall in and collide. You can kind of think of this like if you have a weight on the end of the string that's like swinging above your head. The faster you spin the string, the stronger you have to pull on it in order to stop it from flying off and hitting someone in the head. Okay, so the stronger the pull, the faster the thing needs to orbit. Now, our planet, our star, lives in a galaxy called the Milky Way. This is not a picture of the Milky Way, but it's a picture of a galaxy similar to the Milky Way. And our galaxy, the Milky Way, contains over 200 billion stars, all orbiting each other by the force of gravity. And so what we can do is we can actually go out and look at all of the mass we can see, all of the stars, all of the gas, all of the dust, and calculate the force of gravity from all of that visible stuff and try and predict how fast something would need to be orbiting in order to stay in orbit around all of that gas and dust and stars that we can see. So this is a graph showing those expected velocities. The horizontal axis here showing distance out from the center of our galaxy in thousands of light years. And then the vertical axis here is showing the expected orbital velocity in kilometers per second. And this dotted line here, you can see, is what we expect the orbital velocities to be based on all the matter that we can see, all the stars and all of that. But then we can go out and actually measure these velocities in real life. And when we do that, something surprising happens. So these points here are the velocities that we actually see. The yellow points are the velocities of stars orbiting closer in our galaxy. And then farther out, when there aren't that many stars, we can look at the velocities of clouds of gas. And you can see that the velocities are way, way higher than we expected them to be. Things are orbiting around our galaxy around twice as fast as we would have expected them to be orbiting. And this is a pretty kind of shocking result. This discrepancy in the orbital velocities was first really measured in the 1970s by an astronomer named Vera Rubin. And she deduced that in order for things to be orbiting this fast, there must be a bunch of extra mass exerting a gravitational pull on all those stars, keeping them bound in the galaxy even while they whiz around super, super fast. And today we call this extra invisible mass dark matter, a bunch of invisible mass that we cannot see. Now, these galaxy rotation curves were kind of the first big evidence of some sort of dark matter living in our galaxy. But since then, there's been a bunch of other sort of lines of evidence. So we're not just, trusting this all on one observation. There are a bunch of different detections that we've done that support the existence of dark matter. So for example, in addition to looking at stars orbiting within a single galaxy, we can kind of zoom out and look at entire galaxies orbiting around each other. And when we do this, we see the same thing. They are orbiting way too fast to be gravitationally bound by just the mass that we can see. There needs to be a whole bunch of invisible mass exerting a gravitational pull in order to keep these galaxy clusters bound together. So that's some evidence for dark matter. In addition, we can zoom out even further to look at the largest possible scales in our universe. And we can see here the galaxy clusters all clustering in sort of shapes and strings and sheets and filaments. And based on this clustering pattern, we can infer the existence of this kind of a background clustering, kind of like a scaffolding of invisible matter guiding the formation of the structure that we can see. And that's dark matter. In addition to looking at the gravitational impacts of dark matter on stars and galaxies, we can also look at the gravitational impact on light itself. So if we look at some background source, we can see that the light that it emits gets bent around large clumps of something in the foreground. And there's not enough mass we can see there in order to bend the light that much. So we know that there must be some invisible dark matter there as well. And the last piece of evidence I'm going to mention is that we can look at the ripples at the very beginning of time, the very early universe. This picture here is a snapshot of the very early universe, very soon after the Big Bang. And these little blue and red spots that you can see there are slight ripples over and under densities. And the physics gets a bit complicated here, but basically astrophysicists can look at this picture with the ripples and figure out that in order to explain the patterns that you see in there, you need some type of matter to be there that doesn't interact with light. Otherwise, the patterns would look very different. And this is dark matter again. So we know it was around at the very beginnings of the universe. It didn't just pop into existence recently. So there's many lines of evidence that hopefully have convinced you at this point that dark matter probably exists. There's something out there that has mass, but that we can't see. So I think it's good to sort of take a second and take stock and just go over what do we know about dark matter and what don't we know. So let's start. What do we know? We know it has mass. And sort of connected to that, we know it interacts via gravity. It exerts a gravitational pull on stars and stuff that we can see. We know it's dark. We know it doesn't seem to interact with light. We haven't seen it interacting with light. That doesn't mean it never does. We haven't seen any light interactions. Similarly, it doesn't seem to collide with regular matter. If a clump of dark matter passed through the Earth, we don't think we'd be able to tell. Again, it doesn't mean it never does, but we haven't seen this happening. It doesn't seem to do any collisions with regular matter. We know roughly how much of it there is. This is where I got the number I mentioned earlier of it outnumbers us around 7 to 1. We know roughly where it is. We know what sort of clusters around where galaxies are, and it's a bit less common out in the boonies where there aren't any galaxies. And we know it's existed for most of the history of the universe. Remember that picture I showed you of the very early universe? It was around back then, so it's always been there. So this seems pretty good. There's a lot of stuff that we know about dark matter, case closed. We think, we know enough about it. There's also a lot that we don't yet know about dark matter, a lot of unanswered questions. Like, what is it? Kind of the most basic, obvious question. Where did it come from? How does it fit into our understanding of particle physics? How does it connect to all the matter, the atoms, the subatomic particles that we know here on Earth? How does dark matter fit into that picture? Is it just one type of particle? Or is it many different types of particles? Are there many different kinds of dark matter? We don't know. How massive is each individual bit of dark matter? We know roughly how much in total there is, but is it a lot of very light, tiny particles, or is it just a few big, heavy glomps of dark matter? No idea. Does it interact with itself? So we know it doesn't seem to interact with us, but if two clumps of dark matter try and pass through each other, would they just pass through or would they collide? We don't know. Can it form complex structures like stars or galaxies? Are there dark galaxies out there? Are there dark atoms out there? Can it form chemistry? We don't know. We have no idea. Can it interact at all with regular matter? Like even just very, very weakly? Or is there any way we could possibly, touch it, even if just very, very faintly? We don't know. So basically what I want to talk to you in this talk is how do scientists answer these big questions, which ultimately all kind of boil down to what is dark matter? Or phrased a slightly different way, what does dark matter do? These are big questions. They're kind of intractable. How do you even start going about answering a question like this? And what I'm going to argue in this talk this evening is that it's actually more productive to rephrase these questions in a different way. So instead of asking what is dark matter and what does dark matter do, it's a lot more productive to frame them as what isn't dark matter? What doesn't dark matter do? And so why is it important to try and do this frustrating thing of inverting these questions into the negative? Well, the answer of why this is so much more productive ultimately requires a bit of a detour into talking about the philosophy of science. So to start off our little detour into the wonderful world of the philosophy of science, I'm going to introduce you to this gentleman, who is Sir Karl Popper. Sir Karl Popper is one of the most prominent philosophers of science of the 20th century. A philosopher of science is just someone who thinks deeply about what is science and what makes science science, what makes scientific knowledge scientific. And Karl Popper's big theory that he proposed was that what makes scientific theories scientific was that they could be falsified. For every theory, there is some possible observation you could make, which if you did, would render the theory false. And what this implies is that science can never actually prove something is true. It can only ever prove what was false and what wasn't yet proven false. So the best you can really say for a scientific theory is that it has not yet been proven false. So this is kind of abstract and kind of hard to wrap your head around. So to try to kind of explain what this idea of falsifiability means, I'm going to try and walk you through kind of a practical real life example, try and see what this actually looks like in practice. And since I am unashamedly a 7-year-old at heart, my practical real world example will involve dragons. Excited? Okay, let's go. So the way it works is that imagine a scientist comes up with some theory about how the universe works. Let's call this theory T for theory. So in our example, let's say I propose that there is an angry fire-breathing dragon that lives on my street. Okay, it's a theory. So then in order for this theory to be scientific, it must be falsifiable. It must have some testable prediction. We'll call this prediction P for prediction. So in our example, I would say, okay, if an angry fire-breathing dragon lives on my street, then we should see houses spontaneously going up in flame every now and then. Seems pretty reasonable. So then what do? Then we go and look at reality. If we fail to observe this prediction in reality, then we know the theory must be false, or at the very least in need of some modifications. So if we look around and see no houses going up in flames ever, then we can say with a pretty fair degree of confidence that there is no angry fire-breathing dragon living on my street. We could try and modify the theory, maybe to try and get around this observation. Maybe there is a dragon, but it just doesn't breathe fire. Maybe there's a fire-breathing dragon, but it's just very mild-mannered and doesn't like attacking houses. But at the very least, we've been able to kind of constrict the range of possible dragons that could live on my street. We know that there are no angry fire-breathing ones, which is something. Like, we're able to say something conclusive, so that's good. On the other hand, if we do observe this prediction, all of this tells us is that the theory is consistent with reality, not whether it's capital T true. So if we do see a bunch of houses spontaneously going up in flames, maybe that's because there's an angry fire-breathing dragon living on my street, or maybe all the houses in my neighborhood just have bad wiring, or maybe there are angry fire-breathing goblins. You know, we don't really know. So of these two results, observing the prediction or not observing the prediction, you would think that this one is the more exciting one. You know, maybe it's dragons, but maybe it's not. You know, we haven't actually shown anything conclusive with this result. Whereas a negative result is, I would argue, it's actually a lot more interesting, because now we're able to say something conclusive about what doesn't live on our street, which I would say is a lot more interesting. You actually have been able to say something solid. Okay, so this has been a fun sort of detour through the philosophy of science, but I'm sure some of you are probably asking, okay, what does this all have to do with dark matter? And the reason this is so important for dark matter is that particle theorists, who are people who think deeply about the nature of matter and space and time and reality and all of that stuff, have dreamt up many, many ideas for what dark matter could be. So you can see in this figure here that I found online, it shows the number of theoretical physics papers published on various topics over time. Some of you might have heard of supersymmetry or the Higgs boson. And this black line here that just keeps going up and up and up is the number of dark matter theory papers published every year. This plot only goes up to 2015, but already there are around 1,000 dark matter theory papers published every year. And the number has probably just kept growing ever since. This is a fun but slightly overwhelming diagram showing a small sample of the possible dark matter theories that are out there. Around the outside are a bunch of different topics that theoretical physicists like to think about. I don't know what all of these are, so don't ask me questions about specific parts of this diagram. But inside the red contour here are all the different possible particles which could be dark matter arising from all of these various theories people have. And there are a lot of them, and this is just even a small sample of the total range of theories that are out there. And the thing is, most of these theories are consistent with observations. They make predictions that we do see. They explain all the stuff that we do see in the universe. So to say that some particle could be dark matter really isn't saying very much. sometimes I hear people, say, "Oh, have you heard of this crazy new theory of dark matter? It explains everything. This will change science." Oh, great. You explain everything. Join the club. There are so many theories out there that are able to successfully explain all the data we have about dark matter, that it's not really that exciting to say that you have a theory that successfully explains everything we've observed. It's kind of boring. I would say that it's actually a lot more interesting to try and cross some of these options off the list, to say, okay, maybe we don't know what dark matter is, but we know it's not that, or we know it's not that, to try and rule down this huge, overwhelming list of what dark matter could be. Okay, so we want to narrow down this list of what dark matter could be. How do we actually do that in practice? Well, this is the kind of work that I do as part of my PhD, working to, as Karl Popper suggests, make testable predictions and compare them to observations. On a day-to-day basis, this generally involves a lot of math and computer simulations, but I want to try and walk through an example with you of how this would work for a certain theory of dark matter, based on a project that I worked on recently, a paper that me and some collaborators were able to publish. So this example that I want to walk through with you involves a theory of dark matter that actually did appear on that diagram earlier. It's called quark nuggets. And quarks, some of you may know, are basically the fundamental building blocks of atomic nuclei. Quarks are the things that make up protons and neutrons, and it's the protons and neutrons that make up the nucleus of all the atoms in your body. So they're kind of like fundamental particles. And some theoretical physicists have proposed that if you get a bunch of these quarks together, you could form kind of a big, giant glob of quarks that would be very small and dense, which could be dark matter. It would act like a massive component in our universe that we couldn't really detect. So it's a theory, and these quark nugget models typically have a wide range of possible sizes and shapes. But just to give you a sort of a concrete example of one type of quark nugget that could be out there, these are the sort of things. Their size would be around the size of a red blood cell, which is around 1% the size of a grain of sand. So tiny, 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 but still really large for a subatomic particle. Considering how much larger a blood cell is than an atom, this is huge for a bunch of quarks, but still pretty small compared to us. Now, although it's so small, it is super, super, super dense. So that tiny red blood cell of matter has around the same amount of mass as a dairy cow. So we have a dairy cow's worth of mass compressed into the size of a red blood cell. Oh, and to top it all off, this thing is speeding through our galaxy at speeds of around 600 times the speed of a bullet. So to call this thing a cannonball is a bit of an understatement. But it could be dark matter. This could be that missing component that we've all been looking for. These just tiny, dense globs of quarks. So what me and my collaborators were able to show is we were able to find a new testable prediction for this model. And our prediction was, okay, let's say we have a quark nugget that's floating through space, floating through our galaxy. If this quark nugget hit our atmosphere on Earth, as it's barreling down through the sky, it would strip the electrons away from the air molecules in our atmosphere and leave behind it a very thin, straight trail of plasma. Plasma is basically like a gas where the electrons have become separated from their atoms. They're just free to wander around. So leave this thin trail of plasma. And plasma is interesting because since all these electrons have been split from their atoms, they're free to wander around, just like the metal in a wire. So it's now a conductor. So what happens if we have this long, thin, conducting trail in the middle of a thunderstorm, like we're having tonight here in Toronto? So if this happened during a thunderstorm, thunderstorms tend to have large buildups of positive and negative charge in different parts of the storm, either on different clouds or between the cloud and the ground. This is how lightning strikes happen. Now, if we got this, thin trail of plasma in the middle of a thunderstorm, charge would start to flow along it like a wire. A lot of charge would flow along it. And so this huge electrical discharge would basically look like a lightning bolt, except that it's perfectly straight. It's going right along, following the path of this quark nugget. So a perfectly straight trajectory down through the atmosphere. So this is our testable prediction. If dark matter consists of quark nuggets of a certain size and mass that we calculated in our paper, then we should expect to see the occasional straight lightning bolt. Around 1 in 10 million lightning bolts should be perfectly straight. Okay, so now what most of you should probably be asking yourself is, have we ever seen a perfectly straight lightning bolt? Time to compare our prediction to reality. So my collaborators and I started looking for straight lightning bolts, and we used a highly advanced image searching algorithm called Google to see what the straightest lightning bolts online were. And this is what we found. This is a video that was taken a few years ago over Zimbabwe that appears to show a lightning bolt that is very straight. Kind of weirdly straight. If any of you have seen normal lightning bolts that are all branched and forky, like this should look kind of weird. So then the question was, okay, it looks pretty straight. Is it straight enough to be the trail of a quark nugget? I don't know. I mean, you can look at this, you can try and figure it out. We were able to estimate, what the wind speeds would be and stuff like that. And we concluded that this lightning bolt is probably not straight enough. You can see some little wiggles around the middle there, and we determined those little discrepancies, those wiggles, are too large for this lightning bolt to have been caused by a quark nugget. But that being said, that doesn't mean that we couldn't see one in the future. So I know there is a large community of storm chasers and amateur lightning photographers out there. So if any of you are watching this talk, I encourage you, if you have any photos of your own of straight lightning, please send them to us. We would genuinely be very interested in looking at the straightest lightning bolt you have. If anyone goes out tonight, looks at the thunderstorm, let us know if you have a good picture of a straight lightning bolt. Because it's hard to look for these things all over the planet at once. But okay, so this is probably not a straight enough lightning bolt. But we can ask, okay, what if we did observe a perfectly straight lightning bolt? What if one of you went out tonight in Toronto or anywhere else and took a picture of a perfectly straight lightning bolt? Then what? Maybe it's quark nugget dark matter. Maybe we've just discovered what dark matter is. That would be a Nobel Prize worthy discovery, to say the least. But maybe lightning just behaves weirdly. Like, there's a lot we don't understand about, a surprising amount we don't understand about lightning, really. So it could be that sometimes lightning bolts are just really straight. Without more analysis, we wouldn't necessarily be able to say. On the other hand, what if we never observe a perfectly straight lightning bolt? What if we're able to, hijack all the weather satellites all over the globe and get high enough resolution and look at every single lightning bolt happening on the planet and are able to say with confidence, lightning is never perfectly straight? That's actually a much more interesting result. Maybe it's not as exciting, but it's a lot more meaningful, because now we can actually say with certainty the dark matter cannot be quark nuggets. Or at the very least, it cannot be quark nuggets with a certain size and mass that I mentioned earlier. So this is this kind of form that most dark matter results take. That, here is a prediction that we don't see. We can start ruling out some of the possible range of models of what dark matter could be. And the way scientists typically communicate this sort of a negative result is with something called a constraints plot. This is a very useful tool for dark matter science. So I'm going to kind of walk you through this plot. So this figure here shows all the possible quark nugget models that could be out there, that could possibly be dark matter. The horizontal axis here is the mass of the quark nugget in grams, and the vertical axis is the size, the cross-sectional size in square centimeters. So that example that I mentioned earlier with the red blood cell with the mass of a dairy cow, that one example would show up right here on our plot. And you can imagine that every other single point on this plot corresponds to some other possible quark nugget that could be out there. And so every time scientists are able to figure out some new testable prediction from this model, they can start to rule out some regions of this plot. And we communicate all of those results like this. So this is a bit overwhelming. There's a lot of different shapes on here. I'm not going to explain what all of these are, but basically each shaded region of this plot is a region of this parameter space that we have ruled out by some method. We know for certain that dark matter cannot be something there. So it's kind of like, you could think of it like a giant scratch card, where we're just scratching out different regions, and maybe we'll get the jackpot and discover dark matter, but in reality, we'll just get a bunch of please play again, please play again, please play again, ruling out what dark matter isn't. And so this black region here, the black crosshatched region, this is the region of a parameter space that we can rule out if we were able to say with certainty that there is no straight lightning on Earth, which is something. We're able to try and cut down on that empty space. The light blue region on this plot is similar, but if we instead looked for straight lightning on Jupiter. Yes, lightning on Jupiter. This is the thing. The Juno probe has detected evidence of lightning bolts happening on Jupiter. We don't yet have high enough resolution to tell whether these lightning bolts are straight or not. But if we do in the future, since Jupiter is so much larger than Earth, it's a much more effective probe. And we're able to rule out a much larger region of this theory parameter space. So with this, we're able to say something, kind of conclusive about what sort of quark nuggets dark matter isn't, which is really how most of dark matter science works. So this example of quark nuggets causing straight lightning bolts, it's kind of a niche esoteric example. And it's near and dear to my heart because it's something that I work on, and it's a project that I recently finished. And I think it's a fun kind of illustrative example of how this process of dark matter constraints works in practice. But it's just one example. And so for this last part of the talk, I want to kind of walk you through a few other prominent examples of how dark matter scientists are working to try and constrain some of that vast list of dark matter theories that I mentioned earlier. Okay, so the first sort of test that I want to talk about is terrestrial experiments. These are things that we can physically build here on Earth in very, very, tightly controlled conditions and look at very, very carefully to see, for example, if any dark matter particles occasionally pass through and nudge our experiment a tiny, tiny bit. So this is really useful for probing those theories of dark matter that, interact very weakly with regular matter, just occasionally bump into us. And so this is one example. This diagram here on the left is the super cryogenic dark matter search, which is an experiment that is currently being built to be installed in Snow Lab in Sudbury, Ontario, just a bit north of here. And it's basically a bunch of super cooled crystals inside a bunch of shielding to protect it from the outside world. And scientists are able to look very carefully to see if those super cooled crystals sort of nudge a little bit, see if there's a bit of dark matter that could be bumping into it. And there are a bunch of experiments like this being built all over the world, taking measurements. And so this plot here on the right is another constraint plot, kind of similar to the one I showed you earlier. So again, the horizontal axis here is the particle mass. The units are a bit weirder than grams, so don't worry too much about the units here, but they're of a mass of like tiny subatomic particles. And the y-axis here is basically the probability of it interacting with regular matter. So is it going to interact a lot with regular matter or interact very, very rarely with regular matter? And each of these lines here with these weird looking acronyms is a different experiment that's being built or is currently under operation to look for these dark matter interactions. So you can see the beige here for the super CDMS that's happening in Sudbury. And the region up here in the top right is the region that's been ruled out. We know dark matter cannot be up here. But as we build better and better experiments, we can push those constraint curves lower and lower and lower and try and rule out weaker and weaker and weaker interactions. And it's really hard because you need to, if you want to look for very, very rare interactions, you need to have really well-controlled equipment. But that's what people are doing, and they're making a lot of really good progress on trying to rule out, the dark matter isn't any of the theories up here. So that's really productive to look here on Earth. But we can also look out and look in space at various astrophysical observations. And this is where we first detected dark matter, so we should look there again to look for more of its properties. And the various astrophysical observations of dark matter, this ranges, there's a whole bunch of possible things you can do. You can look at, individual stars and star formation. You can look at galaxies and orbits within galaxies, and you can look at on even larger scales at, entire clusters of galaxies moving around each other. For this section, I'm going to focus on one very famous example, looking at clusters of galaxies. And this is called the bullet cluster. Some of you may have heard of this. If you want more information about the bullet cluster, would recommend you go check out another video on this channel. Mubdi Rahman's A Picture in 1,000 Words is an excellent video about the bullet cluster if you want to know more. But the basic idea is you can see on the left here, the bullet cluster is actually 2 clusters of galaxies. These little orange and white dots are each an entire galaxy. And these 2 clusters of galaxies have recently just crashed through each other. They just collided and passed right through. And so the galaxies themselves are very small and compact. And so they just passed right through. It's like, 2 big handfuls of rocks. They all miss each other and they pass right through. But the hot gas that lives in between the galaxies, this hot gas is so diffuse that it collides with itself. And so we can see this picture on the right. The red and orange blobs are showing where the hot gas is. And you can see that when these 2 galaxy clusters passed through each other, the galaxies were fine, but the hot gas was kind of left behind. It was stripped away and was left behind these kind of 2 trailing clouds behind the clusters. And so that tells us that the galaxies don't interact with themselves and the gas does. And so the interesting thing to look at is, okay, well, what did the dark matter do? And we can look at this by looking at the effects of the dark matter on light passing by, that gravitational lensing example that I mentioned earlier. And these green contours here are basically showing out where we think the dark matter is. And you can see here on the right that the dark matter is with the galaxies. It wasn't stripped off and left behind. And this is really interesting because this tells us that the dark matter didn't interact with itself. Okay, like it might have interacted with itself, but it didn't. And so this non-detection of self-interaction allows us to put constraints on yet another constraint plot. This is similar to the ones I showed you earlier. Again, the x-axis here is the mass in weird particle physics units. And now the vertical axis is the probability of self-interaction. And this whole kind of turquoise region up here is the region of parameter space that we can exclude by this bullet cluster measurement. We know that dark matter cannot interact with itself stronger than that amount. So we're able to put some meaningful constraints on this other completely different parameter by looking at astrophysics, which is super useful. And there are many, many more examples of constraints that you can do looking at various astrophysical objects. Okay, the last example I want to talk to you about dark matter constraints is we're going to zoom out yet again to look at cosmology. Cosmology is the study of the universe as a whole, not looking at any individual object in it. And by looking at the universe as a whole, we can look at how matter is clustering and clumping, regular matter and dark matter, on kind of the largest scales. And so this picture on the right shows a galaxy survey. Every single dot on that picture is a galaxy. And you can kind of see some clumpiness, some patterns of things sort of clustering together. And they're clustering because of the blobs of dark matter exerting a gravitational pull on all those galaxies that we can see. And so from this, we can measure this clumpiness of dark matter, and we communicate this using a very useful type of graph called a matter power spectrum, which basically tells us how clumpy the dark matter is on different scales. And that's this plot here. Each of these colored points is a different way we have of measuring the clumpiness of our universe on many different scales. The y-axis is obviously how clumpy it is, and the x-axis is the different scales, looking, is it more clumpy on big scales or more clumpy on small scales? And you could probably immediately see that this is an incredibly useful tool for dark matter science. This clumpiness that we're looking at is the clumpiness of the dark matter. So you can imagine that different theories of dark matter will make different predictions for how clumpy it will be. Some models will predict a smoothing of clumpiness at really small scales, which we don't observe. We kind of observe a smooth, predictable kind of lump. And we can test all kinds of theories with a plot like this. So there's a lot that we can learn by looking at cosmology, at the universe on the largest possible scales. So far, this has been a lot of negative results. We looked for straight lightning and we didn't see it. We looked for dark matter interacting with our experiments in a lab and we didn't see it. We looked for dark matter interacting with itself and we didn't see it. We looked for dark matter doing something weird with that matter power spectrum, the clumpiness function, and we didn't see it. So you might think that this is a bunch of dead ends, but hopefully I've shown you today that this is actually really exciting. This is exactly how science is supposed to work. According to Popper's view of the falsifiability of science, this is what should be happening. We are actually making a lot of really, really important progress figuring out what dark matter isn't. And that's why I titled my talk that. Okay, so in conclusion, what are a few kind of takeaways that I hope you're able to take away from this talk? The first conclusion is that our universe contains a lot of mysterious, invisible stuff called dark matter. Scientists have lots of ideas about what this dark matter could be. So it's really important to try and narrow down this list of possibilities. Scientists, such as myself, do this by making testable predictions and then comparing to observations, trying to constrain the various properties that dark matter could possibly have. Someday, hopefully, we may be able to narrow down this list of possibilities enough to say with confidence what dark matter actually is, but for now, we're still in the dark. Thank you very much for watching, and now I'll take any questions if there are any in the chat.
Ooh. I was frantically typing as you were finishing, and I'm like, oh, inviting more questions. Here I am. didn't want to leave you in the dark, so to speak. But you made the joke. I can't make it twice. So I am, let's see. Oops. I am going to just make us bigger so that so everybody can see us.
Great.
We do have this is live, and I'm, for whatever reason, it's hiding to stop screen sharing. So that's fine. We'll start on the questions, and then while you're answering, I'll make us bigger, I promise.
I think I stopped the screen sharing on my end.
Oh, maybe stop it on your end.
I think I've already stopped it on my end.
Have YouTube.
I don't know.
Oh, there we go.
Oh,
you win.
Amazing.
I'm gonna send cookies to Harrison's house now, so thank you.
I'll hold you to
it. I'm Uber eating some right now. So we have some really excellent questions that were coming in throughout the presentation. Friedel asks, along the electromagnetic spectrum, there are other wavelengths of light other than the visible part of the spectrum, as we know. Have people thought about using microwaves or X-rays or radio waves to find dark matter? Have they tried that? How did it go?
That is an
Was it
excellent
a terrible
question.
idea? Was it? I know that was a great question.
That's a really great question. Yes, there are lots of types of light that we can't see with our own eyes, like you said, infrared or radio or X-rays. And yes, scientists do a lot of work in these other wavelengths. And so far, we haven't seen dark matter emitting in any of those wavelengths or absorbing, but we can use those wavelengths to tell us a lot of interesting stuff about what the dark matter is doing, to kind of infer what it is doing. So for example, that picture that I showed you near the beginning about the very early universe with the ripples, that's not actually a picture taken with visible light. That's a picture taken with infrared, almost like radio light. So it's light that we can't see, but we can detect it and use that detection to infer that the dark matter is there. Another example is the bullet cluster that I mentioned a bit later. We were able to see those kind of orangey clouds of the hot gas. And the reason we could see those was because of the X-rays that they were emitting. So that's actually an X-ray image looking at those clouds of hot gas. So again, we can't actually see the dark matter with these other types of light, but we can do a lot of really useful, important science with those other wavelengths to help inform us, to help infer what the dark matter is doing. I hope that helps answers the question.
Cool. No, that was, a great question and great answer. Jay asks, does this theory assume that dark matter quark nuggets would interact with other would interact with our atmosphere in the same way as normal matter? And is that a safe assumption, or once again more unknowns?
Yeah. So one of the key features of this quark nugget model is that it's made up of regular quarks. It's not one of the appealing features of this model is you don't need to introduce any weird ghostly particles. You can actually make it with regular quarks, And even these quark nuggets are so small and compact that we wouldn't have seen them when we were looking for stuff. But since they are just the same quarks that we have in our in our atoms, in our atomic nuclei, we predict that yes, they should still be able to interact and kind of collide with the electrons of our atmosphere as they're passing through. And that is kind of the key detection feature of this model that we're looking for. So for this model, yes, it's a safe assumption. For dark matter in general, not necessarily. I mean, different models make different predictions for whether or not they should interact with us. But for this specific model, that's kind of a key feature of it, yes, that it should interact with us.
Cool. We have so many great questions today. Our viewers, they ask such great questions all the time. Cheesable. Oh, I like that nickname. Cheesable asks, is there another dark matter theory that you know of that you consider unlikely or that you think could be disproved? Like maybe there's one right now that people are rolling with, but you're screaming in the back of your head, no, it's not right.
It's a very good question, Cheesable. So there is one model that is kind of having a lot of popularity right now that me and some others are working on, is looking at very, very, very light particles, like super, super, super light. So like what an electron is to us, they are to an electron. And these super, super, super light particles have a good observable prediction that they kind of smooth out the clumpiness of matter on small scales. And some recent work has kind of shown that in the mass range where these things are really interesting and likely, we don't see that smoothing out. We don't see the smoothing properties of this model. So, some people are kind of still looking at it, kind of poke holes in that observation, trying to say, oh, maybe they're not actually measuring what they think they're measuring. But I think that model, at this point, it's probably not 100% of the dark matter, but it could still be a subcomponent. And that's where I think things could still be interesting, that I think people should kind of rotate to focus more, that maybe this type of particle still makes up 10% of the dark matter or 1% of the dark matter. Any one of these theories, even if you've ruled it out at the 100% level, you could still look for weaker effects at the subcomponent level. So that's a theory that, I think hoping for it to be 100% of the dark matter at this point is running onto unsteady ground, but that doesn't mean there still isn't more interesting science we can do by looking into it. So I hope that helps.
Yeah, no, that's great. Here's a basic one, but I also I love this question. What's your favorite aspect of studying dark matter? What do you like about it the most?
Well, I am a big fan of fantasy and sci-fi, and I really like sort of the creative aspects of it, trying to imagine hypothetical worlds and trying to figure out what it's doing. And in my mind, that's basically what a lot of dark matter science is. You're not necessarily working with reality, which I think could be discouraging for a lot of people, that you're working on these theories that might not be true. But I think it's actually really fun and interesting. You're taking this kind of hypothesis and you're imagining, okay, what would happen if dark matter were this theory, and then at the end we can try and see whether it actually corresponds to our reality. But we're working in this kind of this fun space of these theoretical ideas and trying to logic through what the implications would be, which I think is really fun.
Yeah, no, that, like I said when I was so excited to introduce you, this is one of those things that everyone seems to love to talk about, and I think it's because still it's such this mystery fantasy type thing.
Oh yeah, it's completely unknown. Anything goes, really.
Yeah, which I love about it. Science isn't just in a box. It could be anything. That's, I think, why I love it. Maybe that's why a lot of people love it and are so interested in it. So I love this question because if nobody else was gonna ask this, I was gonna ask my own question, because I feel like I'm allowed one question. But Daniel, you beat me to it. What could be the possible ramifications of sufficiently constraining theories of dark matter? I was going to ask this because I really wanted to know what happens if you finally figure it out.
Well, if we do finally figure it out, that would be amazing. It would kind of involve a complete reversal, a complete paradigm shift of how we think about fundamental physics, because we have to kind of completely restructure our understanding, or I expect we'd have to restructure. Maybe this isn't a guarantee, But I expect we would have to restructure our understanding of particle physics in order to include whatever this new dark matter theory is. And the implications of that, I mean, you can imagine how the transition from classical Newtonian mechanics to quantum mechanics ushered in, electronics and GPS and nuclear power and all kinds of crazy things. So any sort of a major paradigm shift in our understanding of science like that, it's hard to say ahead of time what implications that would have, but I imagine they would be huge. Being able to, if we did have some way of interacting with this dark matter, some way of gaining energy from it, could we maybe gain energy from the flow of dark matter through our galaxy, or use it to send signals, communication? Who knows? I mean, the sky's the limit, really.
Yeah, no, that's wild. That's wild. And that would be something, that I would just mull over and lay awake thinking of, what happened.
Yeah, it's probably not gonna happen anytime soon, but when it does happen, it would be super exciting.
Yeah, no kidding, exactly. So somebody is asking about this. About the lightning bolt. The I was arguing with Harrison when we met, and I got a little sneak preview of the talk. I'm like, that lightning bolt was very straight, but apparently not straight enough. But straightest lightning bolt I've ever seen. But there's a question: shouldn't we be able to see the straight quark nugget lightning bolt even if it isn't cloudy? I was
even if it isn't cloudy. Oh, so if it isn't a thunderstorm. Yeah, so the thing, what would happen if it wasn't a thunderstorm, it would still leave behind a thin ionized trail. But most likely this trail would be so small that we wouldn't actually really be able to see it. What we see in the straight lightning bolt is not the quark nugget. What we see is the electrical discharge flowing along the path of the quark nugget.
Okay.
So in a lightning storm, we have big bunches of positive and negative charge built up that are able to flow along this wire. And that's what we actually see. We see that electrical discharge like a lightning bolt, because it is basically a lightning bolt. Whereas ordinarily, with just a clear sky, you would need a really, really big quark nugget to actually, be able to see it like a meteor. And that region of the parameter space has already kind of been ruled out. So we know there aren't any quark nuggets out there big enough to cause big flaming meteors. But it could still form these little thin ion trails that could still form lightning bolts. So that's still something worth looking into.
Okay, so that makes sense. I just also like saying quark nugget.
It's
such a fun word to say. It's very fun. That would be a good band name, Quark Nugget. This is, here's another broad question, but another really good question. Amy asks, why is it so important, for scientists to study dark matter?
Well,
it's a big question, but
what
is your opinion?
So, I think the reason it's so important is probably the same reason that, that example that I told you at the beginning of all those invisible people. If you were told that there were 45 billion invisible people on our planet, would you not consider it a priority to try and figure out who these invisible people were? Would you be content just going about your day saying, okay, fine, I am only able to see 1/8 of all the possible people here on the planet, and I'm good with that. I'm happy with this big absence in my knowledge.
No, I would not be satisfied.
I know, me neither. I'd be like, who are these people?
Who are they? Tell us now.
Dark matter can seem kind of, abstract because it's out in space and we can't see it. And, what does that matter to us? But I think the fact that we only really understand 1 part in 7 of all the matter that we can see in the universe, that should be troubling to people. That's a huge gap in what we know. And maybe there won't necessarily be tech spin-offs of this research immediately, but I think it's sort of the prerogative of science to kind of look at the questions that we don't understand and see if we can try and pick away at it, see what we can figure out, kind of add to our collective body of knowledge, and try and see if there is anything useful out there. Or just to wonder at what is out there, because it's probably amazing, whatever it is. So I think that even though, it may seem kind of abstract and hard to really understand why we're doing this, I think that the fact that there's so much we don't know should be enough of a reason.
Yeah, no, that's great. And the analogy with the people too. No, that's a great answer. Obviously, exactly, you'd want to know there was that
I would
much
want to know, yeah.
invisibility. I would want to know too. Like, are they all wearing Harry Potter
I
invisibility
don't know.
cloaks?
Can I
Like,
become
don't know.
invisible? Like, I want to know this.
Yeah, exactly. I mean, it's cool.
Yeah.
So Dorsa asks, she says, or she or he, I'm not sure. This is going a bit off topic, but I'm wondering if there has been any observations of the of gravitational waves, which we've had several people come on and talk about gravitational waves. But in terms of gravitational waves, have those told us anything about dark matter, or can they measure or show us anything, or is that maybe something completely separate?
That's a great question. I mean, the thing with dark matter is it's such a broad area of research that you can use basically anything to study it, whether it's, you know, galaxies or lightning bolts. So yeah, totally. Gravitational waves are super useful. The fact that we've observed so many gravitational waves at this point, we can start looking at things like, you know, how the gravitational wave is propagating through space, stuff like that, to try and understand where the dark matter is potentially. But one really big thing that gravitational waves are able to do is they're able to tell us how many black holes are out there in the universe. Mm-hmm. And this is useful because black holes for a while were actually, still are, I guess, are a possible model of what dark matter could be. Because, you know, they're massive, we can't see them. Maybe they're dark matter. And this was ruled out in maybe the 90s, because people started looking for black holes that were similar mass to stars that we see around us. Looking at their effects on light from background stars, it gets a bit complicated. But we were able to rule out stellar mass black holes from being the dark matter. But now with all these new gravitational wave detections, the interesting thing about them has been that the black holes involved are typically a lot more massive than we thought that black holes should be able to be. And so maybe there's just something about you know, stellar physics and black hole formation that we don't really understand. Or it could be that there's this big population of higher mass black holes, sort of an outside the window that we were looking earlier, which could be dark matter, either a full component or some sort of a subcomponent. And so getting lots of gravitational wave detection, sort of being able to understand this population of black holes better, can kind of help us figure out, are these just, you know, remnants of old stars, or are there enough out there that maybe they're from some other weird mechanism, and maybe this is some part of the dark matter. So that's kind of a very tangible thing that gravitational waves are able to contribute to a specific theory of dark matter. But in general, they're another observable. They should be useful for something, for sure.
Cool. And then once again, the other thing that I've learned in my time in the astronomy department is everybody loves a good old-fashioned massive black hole.
Love a black hole.
We love them. We love them here.
Never have too many of those.
No, exactly. Those are some of our most popular talks. Like, let's talk about black holes. We're here for it. So, oh my, all these questions are so good. I'm so proud of our viewers asking such great questions.
Amazing. Gonna be here a while.
Well, I mean, Sue is asking, can ordinary particles decay into dark matter? Do we know? Or?
That's a great question. That's a really good question. We don't actually know. So there have been a lot of experiments at the Large Hadron Collider in Europe. One of the many research programs that they're doing right now is actually looking for dark matter, trying to see, okay, if we collide two particles together, measure all the energy going in and all the energy of things coming out, did any energy leave? Is it possible that something in that weird complex collision turned into dark matter and escaped? It's possible. Like maybe dark matter does connect to our matter, but only in the really high energy conditions of the Large Hadron Collider. So far, they haven't seen anything, which in turn, I mean, that's useful, right? The whole point of my talk is that negative results are really useful, that we're able to put constraints on, you know, what could decay into dark matter, what sort of regular matter could decay into dark matter. But potentially, it's very possible that someday someone will do one of those collisions and say, you know, we didn't get out everything we put in, and start looking for that missing particle that flew off and disappeared. So it's possible, but we don't know.
Cool. No, that's cool. Here's one. This seems like a really hard question, but well, but it's only because I'm the non-astronomer. Jay asks, he asked another great question earlier. Universe clumpiness resembles water refracting light. Is it possible there's no dark matter and clumpiness is the turbulence of the universe itself? Or has that been disproven? Or does he have a valid idea here?
So by clumpiness of the universe itself, I mean the regular matter that we can see probably isn't enough to be causing all the clumpiness that we observe. It by clumpiness of the universe, you could also be referring to the space-time itself, kind of the background fabric on which everything is happening, the stage on which everything is taking place. And if that was clumpy, sure, maybe that could be causing the clumpiness that we see. But again, we're able to test that, and we don't think that it's just increased perturbations in space-time, mostly because in order to curve space-time, you need mass. Like that's what general relativity tells us. And we just don't see that much mass there. So I guess in a sense, it is like they are gravitational potential. Well, it is gravity that's holding it all together, and gravity is just the curvature of space-time. So in a sense, it is space clumping. But in order for space to be clumping that much, again, we need some hidden mass, some extra mass that we can't see. And so once again, we require the dark matter anyway. So either way, it's hard to explain your way around requiring some sort of an invisible mass to provide that clumpiness. That's a good question. People are it's definitely something people have looked into.
I was like, whoa, that seems so hard.
It's a hard one,
but
sure.
that's a hard one to grasp. Looks like we're coming up to we've gone a little past time, so I'm gonna allow us to do one more question before we say good night. I'm curious about this one too, because we've had, a couple radio astronomers on the show in the past, and they talk a lot about like different colors that you see, and this one or don't see, and visible light, etc. So somebody is asking, why is the visible light we can actually see why is the visible light that we can see such a small part of the universe compared to all of this dark matter?
I mean,
it's a huge question.
Yeah, that's also an excellent question. We don't really know why there's so much of the universe that we can't see. Like that's sort of that is the big question. Why can we only see a small part of it? Yeah, I don't have a good answer for you. I mean, yeah, that's basically the big mystery. Why is there so much that we can't see? So I'll leave that question with all of you to ponder until we get a better answer to it.
That's actually that was completely unplanned, but that's actually a really good answer, and actually a pretty good way to wrap up the evening. And I think it is great because it really teaches kind of people, and myself too, as I learn more and more, you're always kind of reaching in science, and there's a lot to celebrate what you don't know. It's just not about acquiring, knowledge. I mean, you still are acquiring knowledge when you don't know.
It's the stuff you don't know.
It's mind-blowing. Yeah. Once again,
yeah,
it's like mind-blowing, like the mind-blowing emoji that I like to use. So yes, we have no that's it. No, we can't top that last question, but we do have cutting it off. No, we have no further questions this evening because you've done such an amazing job of answering them all. So we do thank you for joining us and giving your awesome dark matter talk.
Well, thank you for hosting, and thank you to all the listeners for tuning in.
Yeah, we had a great turnout, and they asked amazing questions, and I love them for that. So next week we are back. We have Dr. John Percy joining us next week, and I think he's now holding the unofficial record. It's going to be his third talk. He just keeps coming back, and we love having him. And so, his talks are always super, super entertaining. So he'll be back next Tuesday at 7 p.m. Eastern. My colleague, Mike, I believe will be moderating. I think we're also going to have another new episode of A Picture in 1,000 Words coming out on Friday. Once again, super awesome. There's lots of archived episodes of both Cosmos from Your Couch. I think we're getting close to our 30th episode, 25 to 30. Yeah. So there's a lot. If you want to binge and have lots of snacks and watch them all, they're there for you. Although, you know, you might be there a while, but also picture in 1,000 words. Lots of archived episodes there. So we do hope that you'll check them out. We have other exciting online events. I'm giving you guys a scoop. I can't say too much yet, but keep following us because we're planning another big online astronomy event for September, because we know how much you guys are enjoying this, and we're certainly enjoying bringing it to your homes kind of while we're not going out as much. So I hope you'll come back and join us. So with that, Harrison and I will say goodnight. Harrison, thank you so much once again. You're a star. I love it. Thank you for making me laugh so much. And I'll debate you forever about that straight lightning bolt. But I will be watching now, as I'm sure most of our viewers will be, for the straightest lightning bolts.
Good.
For now,
if you get a
from the end of
picture,
time.
send it
Yeah, get a picture. I know. I'll send it in. So with that, we'll say good night and hope to see you guys again. Thank you so much for joining us. Good night.
Good night.
Cool, we're off. I was like, wait a couple seconds.